Hi everybody, this is Miss Eisencraft with Unit 1, Lesson 5 practice problems for geometry. So let's start with number 1. Here's a straight edge and compass construction of a line, looks like right here, perpendicular to line AB passing through point C. Explain why it's helpful or why it was helpful for them to construct points D and A to be the same distance. So what they did here is because by making A and D the same distance from C, they made C the midpoint of segment AD. So this made C the midpoint of AD. And then they used perpendicular bisector, what we knew about perpendicular bisectors. So the perpendicular, I'm going to use a symbol, perpendicular bisector of AD would work to not only create a perpendicular line to segment AD, which is on the line we need, and would go through C, because we made C the middle, and we know perpendicular bisectors, we made C the middle of AD, and so we want the perpendicular line to pass through C, which is the midpoint. So we kind of worked backwards to make sure that that would happen. Okay. Number 2, here's another diagram. It's a straight edge and compass construction. Select everything that's true. Line EF right here. Okay. Is this the bisector of angle BAC? So BAC, okay, is this guy out here. Yes, it appears as such. It looks like this is the exact construction we did in class to bisect an angle. I'm going to say yes. Now, is line EF the perpendicular bisector of segment BA? Is it making a 90-degree angle and cutting BA in half? No. Is line EF the perpendicular bisector of AC? Is it making a 90-degree angle or cutting this in half? No. Is line EF the perpendicular bisector of BD? Well, BD, let's go ahead and draw that segment in. Oopsie daisy. Thank you for zooming in. Did not mean to. Oh my gosh. Okay, if that segment was drawn, yes, that red line not only cuts it in half, but makes a little 90 degrees right here. Okay, yes. And is line EF parallel to line CD? No, these do not look parallel at all. No. All right, next problem. We have a straight edge and compass construction. A is the center of one circle and B is the center of the other. By definition, a rhombus is a quadrilateral with 4 congruent sides. How can we kind of prove that's true based on this construction? Well, what we're going to focus on is the radius, okay? AC and AD are both radii of circle A, so we know they're the same. Yes. Okay. BC and BD are both radii of the circle centered at B, so we know the orange has to be congruent to the orange. Well, how can we be sure that yellow is congruent to orange? Well, it's the way the circles are intersecting. They are both sharing a common radius. If circles share a common radius, right, circle A, the circle centered at A has radius AB. The circle centered at B has radius AB. So they have to be the same. So all the radii, all the yellow radii over here have to be the same as all the orange over here. So we could say they are all radii, all those segments. They are all radii, plural of radius, of circles that share a common radius, which means the two circles are the same. A, B, and C are the centers of 3 circles. A, B, and C are the center of 3 circles. Which line segment is congruent to HF? All right, let's see what we got here. So HF looks like, in this circle, it looks like it's the distance of 2 radii, also known as the diameter. So first of all, we can prove that these 3 circles are equal because of their shared radius. So see how radius AB makes the bottom 2 circles the same, because circle centered at A has this radius, circle centered at B has this radius. This one up here, we know it can be congruent to A because it has radius AC, um, and, and that is the same as radius AB. So we know these 2 circles are the same. We know all 3 are the same. So we're looking for line segments that are the length of 2 radii of these circles. So first of all, AB, that looks like just 1 radius. CD looks like 2, but not quite. If you look to the edge of the circle, that's not to the edge of 2 circles. No. How about DF? DF. Oh, hey, radius, radius. Yes. And how about CB? That's the length of 1 radius. It's absolutely not. Okay. Number 5. In this construction, A is the center of one circle and B is the center of the other circle. Explain why segment EA is the same as BC. Okay, we went over this earlier. It's just a little bit different picture. I don't know what happened. EA and BC are both radii, although it's different circles. They're both radii of circles that have a common radius. Both circles have a common radius AB. So therefore we know the circles are the same. So they are both radii of circles with a common radius. Okay. Number 6. Okay. CD is the perpendicular bisector of AB. We know that all of the points on the perpendicular bisector are equidistant to A and B. So, is point M closer to point A or B? Well, point M is on the perpendicular bisector, so it'll be equidistant. M would be equidistant from A and B. So it's the same distance because it falls on the perpendicular, because M falls on the perpendicular bisector, which is the set of all points equidistant from A and B there. Okay. Skip number 7. Last one. Here's a diagram. This was from early on, Unit 1, Lesson 1. Okay. A little bit easier when we were first looking at diagrams here. C is the center of one circle and B is the other. Explain why the length of CB is the same as the length of CD. We don't even need to look at the little circle. Okay, CB is the radius of the circle centered at C, and so is CD. So they are radii of the same circle. They are radii of the same circle, which means they are the same. All right. I hope that was helpful.